Okay, so we ended the last video with this particular clicker question. So let's go ahead and work the problem. The first thing I want to ask you is this question asking for an average rate of disappearance, or is it asking for an instantaneous rate of disappearance? Well, an instantaneous rate implies one particular moment in time, and this is a range of time. It is literally from 0 to 100 seconds. So it's definitely an average rate, and we would calculate this essentially as 100 seconds. This would be time 2 minus 0 seconds, which would be t1, and that's where we get the 100 seconds for. So this is an average rate of disappearance that's being asked for. We would calculate that simply by the change in the concentration of NO2 divided by the change in time. And so since it's a rate of disappearance, we've got a negative sign out here. This is going to be the concentration at times 2 for NO2, and that's right here, time 2. This is the concentration of NO2 at time 1. And so we're going to have 0.0065 molar minus 0.0100 molar, this is molarity, divided by T2 minus T1, which they've already done for us, which is 100 seconds, no great mystery there. We're going to get a negative sign up here, times a negative sign, which gives us a positive, and we wind up with 3.5 times 10 to the minus 5 molar per second. And that's our average rate of disappearance, okay? Rate of disappearance of NO2 over time. All right, so let's move on. All right, let's talk about stoichiometry and rates. Now, remember what stoichiometry is. You had that last semester in Chem 1, whenever it is that you actually took Chem 1. And stoichiometry is literally the measurement of the elements, and what you remember it as are the coefficients of the different components of a reaction, whether it's, coefficient of 2 reactant A plus 1 reactant B makes 3 reactant A, B's, or whatever the reaction is. That's what stoichiometry represents. Now, we looked at the reaction of methanol plus hydrochloric acid making chloromethane and water, and all of our components in this reaction have coefficients of 1. So the rate of disappearance of methanol will equal the rate of disappearance of hydrochloric acid, which will equal the rate of appearance of chloromethane, and which will equal the rate of appearance of water. And that is only because the coefficient is 1 for all of these. What that means is, in the same period of time that 1 mole of methanol disappears, 1 mole of hydrochloric acid will disappear, and 1 mole of chloromethane will appear, and 1 mole of water will appear. That's only true because the coefficients are 1. Now, what happens when the coefficients are not 1? Well, that's going to change things. So here is the Haber-Bosch process for producing ammonia from atmospheric nitrogen. So the stoichiometry says that 1 mole of nitrogen is required to react with 3 moles of hydrogen, diatomic hydrogen, to produce 2 moles of ammonia. So we definitely don't have a 1-to-1-to-1 relationship here. And this is what it says. For every 1 mole of nitrogen that is used, 2 moles of ammonia are formed. For every 3 moles of hydrogen that are used, 2 moles of ammonia are formed. And for every 1 mole of nitrogen that is used, 3 moles of hydrogen are required. All right, so how do we use this when we're doing kinetics, when we're trying to establish the relative rates of disappearance of our reactants and appearance of our products? So we introduced you last time to graphs and how the slope of the graphs will determine or will give you an indication of the rate, whether it's a fast rate, whether it's a slow rate, and when those rates actually gradually asymptotically approach zero. And we can do that here. So hydrogen and nitrogen are our two reactants, and ammonia is our one product in this reaction. Now, we don't have any ammonia to start with, so its concentration is zero. And we have 1 mole of nitrogen and 3 moles of hydrogen. Let's take a look at the slopes of the curves as the reaction proceeds over time. So here we go. And you can see that because 3 moles of hydrogen are required in this relative to 1 mole of nitrogen, the slope of the curve for hydrogen is much steeper. So that says in the same amount of time, hydrogen is a 3-to-1 ratio with nitrogen. Now, in the same amount of time, 2 moles of ammonia are going to be produced. Eventually, as the reaction comes to a termination, all the rates end in zero. That is, the rate of change of the concentrations of our different components stop changing. They reach a zero rate of change. All right, I've drawn to the best of my ability, which is really pathetic, slopes of the line at time zero, which we call the initial rate method for calculating instantaneous rates. And I think you can see that this instantaneous rate based on the tangent to the slope of these curves at time zero is very steep. It's a very steep slope with a negative slope. So we have a negative slope that's very steep for hydrogen. We also have a negative slope for nitrogen, but it is about 1/3 the slope of the hydrogen molecule, and that's because of the difference in the coefficients here. For ammonia, we have a positive slope, and the positive slope here is about twice the negative slope of nitrogen, because remember, products, they appear, reactants, they disappear. So these will all have negative slopes on the graph, and we'll have a positive slope for ammonia. But these tangents to the curve, and somehow I just lost my tangent for ammonia, and ammonia is about twice the positive slope as that of the negative slope of nitrogen, and so on. So the relative slopes of the curves indicate the relative rates of either appearance for products or disappearance for the reactants. And you need to at least be familiar with how we reference these rates of reaction graphically, because we're going to see them later. All right, so based on the following reaction, the rate at which ammonia is formed is blank that of the rate that nitrogen is used. Now, this is really easy to determine. Since the coefficient of nitrogen is 1 and the coefficient of ammonia is 2, you can see that ammonia is going to appear if I just take any period of time. Let's say 10 seconds of time, I allow the reaction to go forward. Well, relatively speaking, in that same 10 seconds, twice as much ammonia will appear as nitrogen disappears. Okay? And so that's pretty easy to figure out. All right, so go ahead and answer that question as a clicker questions. So let's look at stoichiometric relationships. So here's a general reaction. We have reactant A and reactant B with coefficients lowercase a, lowercase b. products capital C, product capital D with their respective lowercase subscripts. We can relate this rate of disappearance to this rate of disappearance to this rate of appearance to this rate of appearance with the following method. All we do is we take the coefficient, we make it a denominator with a numerator of 1. By this method, what we're able to do is we're able to equalize all the rates for each component in the reaction regardless of what their coefficients are. So this is the method. The minus sign again, that's for the reactants because it's a rate of disappearance. And then, of course, the positive values for the products in the reaction. Okay, let's take a look at an actual reaction, one we should be familiar with. This is the Haber-Bosch process for taking atmospheric nitrogen, combining with hydrogen to produce ammonia, which gets used in fertilizers, explosives, floor products, all sorts of uses for ammonia. So here's the case that we have. The way I want you to think about this is that the reaction is moving in the forward direction. Now, in the same amount of time that 1 mole of nitrogen disappears, because remember it's a reactant, it disappears, 2 moles of ammonia are formed. All right, think about that. So you've already answered a question on this. So if we're talking about the same amount of time, pick any amount of time and just say that 1 mole of nitrogen disappears, 2 moles of ammonia appear. That means the rate of appearance of ammonia is twice that of the rate of disappearance of nitrogen, because 2 moles are appearing in the same amount of time that 1 mole of nitrogen is disappearing. So we can relate these to each other by simply taking the coefficient, putting it in the denominator, and then putting 1 in the numerator. And now we've made an equivalence between the rate of disappearance of nitrogen to the rate of disappearance of hydrogen to the rate of appearance of ammonia. The minus signs for the reactants are, of course, because reactants disappear. All right, so some of this is language, some of this is just understanding the circumstance. We're talking about a unit of time in which this reaction is occurring. So now all of these rates are equivalent to each other. Since ammonia appears at twice the rate that nitrogen disappears, by taking the coefficient 1, putting it in the denominator here, we're saying the rate of disappearance of nitrogen is equal to 1/2 the rate of appearance of ammonia, because ammonia appears twice as fast as nitrogen disappears. So the rates are equal if we have them expressed like this. Now these two rates are equivalent to each other. So let's just say that the rate of disappearance of nitrogen was 1 molar per second. Now we have 1/2, since ammonia is going to appear twice as fast as nitrogen has disappeared, we would have 1/2 times 2 molar per second for ammonia, which would equal 1 molar per second. Now these two rates are equivalent to each other because we've multiplied the rate of appearance of ammonia by 1/2. We've simply taken the coefficient, put it as a denominator here. These two rates are now equivalent to each other. We can do the same thing with ammonia here. So we're going to stick with this. Since the rate of disappearance of nitrogen is 1 molar per second, we would say that the rate of disappearance of hydrogen is 3 molar per second. Now, all we have to do is multiply that times 1/3. The 3's will cancel. We'll wind up with 1 molar per second. All these rates are now equal to each other utilizing this little piece of technology. Okay? All right, so let's see if we can't make some sense of this. We're now going to relate the rate of disappearance of nitrogen to the rate of disappearance of hydrogen. And we're going to relate the rate of disappearance of nitrogen to the rate of appearance of ammonia, and finally the rate of disappearance of hydrogen to the rate of appearance of ammonia. Let me show you how this is going to work. Okay, so let's say what we want to relate is the rate of disappearance of hydrogen to the rate of appearance of ammonia. And let's say that I know the rate of appearance of ammonia, but what I want to know is the rate of disappearance of hydrogen. So this is the rate I know, the rate of appearance of ammonia. I actually have a number for that. I can call it anything. I could say this has a rate of appearance of 3.5 times 10 to the minus 2 molar per second. It doesn't matter what this rate is. I just happen to know it. I measured it in a lab. But what I want to know is, well, given that this is the rate that I know, what is the rate of disappearance of hydrogen? So that's the rate that I want to know. All you have to do is multiply the denominator of the rate you want to know times both numerators. So we're going to take the rate of the denominator of the rate I want to know. We'll multiply 3 times 1/3. The 3's will cancel. And then 3 times 1/2. What we wind up with is that the rate of disappearance of hydrogen is equal to negative 3/2, or 1.5 times the rate of appearance of ammonia. That's what this little piece of technology will give you. Let me do that again. All right? So in this particular case, I know the rate of appearance of ammonia. I want to know the rate of disappearance of hydrogen. So I multiply the denominator of the rate that I want to know. Okay? I want to know this particular rate. Okay? I want to know that one. So I take the denominator after doing this little piece of technology and setting it up, and I multiply both numerators by that denominator. It will cancel here. And I also include the negative sign in that, by the way. And then I will have 3 times 1/2, and the result is that I have the rate of disappearance of hydrogen is going to equal minus 3/2 the rate of appearance of ammonia. Don't forget that we always express reaction rates in the positive. So in our little particular problem, this would really just be 3/2 times 3.5 times 10 to the minus 2 molar per second, which would give me a result. My result would be 5.25 times 10 to the minus 2 molar per second in this particular case. And it's going to work every time, guys. And by the way, the negative sign here, it's really just language. It's asking if you understand what exactly you've done. This still means the rate of disappearance. Okay? So what you're saying is the rate of disappearance of hydrogen is equal to negative 3/2 the rate of appearance of ammonia. For practical concerns and just computing the value, you know you're going to come out with a positive value here. You just multiply 3 halves or 1.5. This is just 1.5 times 3.5 times 10 to the negative 2 molar per second. You get 5.25 times 10 to the minus 2. Okay? That's how that's going to work. So let's work this little problem. The decomposition of dinitrogen pentoxide proceeds according to the following equation. We've got 2 moles of dinitrogen pentoxide decompose to form 4 moles of nitrogen dioxide and 1 mole of oxygen. And the question is, if the rate of decomposition of dinitrogen pentoxide at a particular instant in a reaction vessel is 4.2 times 10 to the minus 7 molar per second, what is the rate of appearance of nitrogen dioxide and then oxygen? All right, so first thing we want to do is set the problem up in exactly the way that we said. All right, so if we go back, we see that we know that the rate of disappearance of dinitrogen pentoxide is 4.2 times 10 to the minus 7 molar per second. So after we set the problem up, we're going to solve for nitrogen dioxide first. We set it up by simply doing minus 1/2. Just take the coefficient, put it in the denominator, 1 in the numerator, times this rate. This is the rate we know. This is the rate we want to know. So what are we going to do to solve this? The denominator of the rate we want to know. This is what we want to know. And we're going to multiply it times both sides. Okay, both numerators. Okay, and when we multiply it times both numerators, it will cancel here. And here we'll get 4 times 1 over 2, which is just going to wind up as 2. So the rate of appearance of nitrogen dioxide is going to wind up being 2 times the rate of disappearance of dinitrogen pentoxide. Okay, and then we'll take care of oxygen here in just a second. So for nitrogen dioxide, we've multiplied both sides by 4. We get this solution, 4 over 2, and then that just gives us 2 times the rate of disappearance of dinitrogen pentoxide. And so that's going to be 2 times 4.2 times 10 to the minus 7, which is going to be 8.4 times 10 to the minus 7. And then for oxygen, we're comparing these two. We want to know this rate. Its coefficient is 1. And so its coefficient its coefficient is 1. So we're going to multiply both numerators by 1. That's going to be 1 times 1 divided by 2. And so the rate of appearance of oxygen will simply be 1/2 times the rate of disappearance of dinitrogen pentoxide. So that's just going to be, that'll just equal 1/2 times 4.2 times 10 to the minus 7. This wound up being 2 times 4.2 times 10 to the minus 7. And it's molar per second. Don't forget your units, guys, like I did. Okay? All right. That's how you work those problems.